and some are bad. But, good or bad, it's that they lurk behind the scenes of all mathematical thought. Ladies and gentlemen, without further ado, please join me in welcoming Professor Douglas Richard Hartle.
Thank you for turning out in such great numbers. I'm very impressed. And today happens to be Bach's birthday, in case you didn't know that. And I might say that it's not a very interesting birthday. I calculated it. Let's see, I think it would be 328. If I said 328 is not a very interesting number, I might be shown wrong if Ramanujan was in the room, so I won't say that. But offhand, I'm not sure whether 328 is terribly interesting. I'm familiar with this kind of lecture named after someone because there's a lecture at Stanford in honor of my dad, an annual lecture, and it's always appreciated when the lecturer can make a reference. It's appreciated by our family, that is. If the lecturer can make a reference to our dad in some way or other. Unfortunately, I didn't know anything about the K-Fitz family. I even would have mispronounced their name. I would have said Key-Fitz. So I'm an ignoramus, and I apologize for that. But I do very much appreciate this honor. And one last thing I wanted to say is, of course, it's a great honor to be asked by the Fields Institute, which I assume is connected with the Fields Medal. It's the same thing, same set.
Connected by name.
Only by name?
They're both named after John Charles Fields.
Yeah, okay, so there's some connection. Well, I'm too old to win the Fields Medal, I'm afraid. But I still do hold out some hope for earning the Pastures Medal. That's something that is, Fields is given only to a mathematician of 40 or younger. But the Pastures Medal is given to mathematicians of 80 or older. And so, in a few years, maybe I will be eligible for the Pastures Medal. I'm hoping to win that one, at least. Now, about analogies in mathematics. I don't think that Raphael was correct in saying that I'm a mathematician or whatever he said. I don't know exactly how he phrased it. But let's say that I have a lifelong love of mathematics. And when I say lifelong, it does go back to when I was like 2 years old. I was convinced I was going to be a mathematician when I was a kid growing up. And eventually, to my chagrin, I hit what I call my abstraction ceiling when I went to graduate school, and it was a very painful experience. But so I didn't wind up becoming a mathematician. Nonetheless, I have retained a very active interest in mathematics, in, let's say, the lower levels of mathematics. I don't go up into the stratospheric heights that people like Andrew Wiles do. But I try to understand as much mathematics as I can. And I've always been a self-watcher, somebody who watches their own cognitive processes. It's just some fact about me that has been the case ever since I can remember. And so I have paid attention to my thought processes in mathematics, in my mathematical thinking. And of course, I have noticed analogies happening all the time. But I've also noticed them in the work of other people who are involved in mathematics, who are professional mathematicians. And so I'm going to talk about all of those kinds of things tonight, and I hope I won't be too long. I wanted to sort of summarize what mathematical thinking is from my viewpoint. I mean, there's a stereotype, I suspect. I don't know exactly how I would phrase it, but it would, I mean, if you really don't know anything about mathematics, your stereotype is ridiculous. It's something like mathematicians are good at doing arithmetic fast or something like that. But, but that's a very elementary or rudimentary or primitive stereotype. But a more sophisticated stereotype would be that mathematicians sit around doing proofs. They prove things. Or they solve problems. I think those are certainly activities that mathematicians are engaged in. They would be on my list, absolutely. They make proofs and they solve problems. But I want to list a few other things that they do because I think that these things are generally not the things that are foregrounded when people talk about what mathematical thinking is. So I put as my first thing on the list, seeking patterns, and I'll give some examples of that. Proving things, okay, I just mentioned that. Inventing concepts, inventing new concepts. Generalizing old concepts. I have the next label is a little blurry, but I call it crisscrossing things. That is, crisscrossing being a verb. In other words, you crisscross two things. Maybe hybridizing or combining or splicing together two things. Perhaps I'll show you some examples of that. Well, I surely will show you some examples of that. But the idea is taking two ideas that are, in some sense, not related and putting them together in some interesting fashion and seeing what results. Okay, solving problems, I said that. Finding minimal and maximal cases or extremal cases of things. Simplifying complex structures by spotting simpler essences in them. And discovering new objects and inventing objects. So those are some of the activities that I see. And in every one of them, analogy plays a central role. And I don't promise that I will go down this list in order because my lecture is improvised and it's not all that well structured. But I will certainly touch on many of these items that I have mentioned as I go through some examples. And I will show how analogy making is involved in lots of these facets. So, we begin, curiously enough, there's a poster that was up on the second floor of the Fields Institute when I was shown to my office, my temporary office, and it says, Ramanujan remembered, or something like that. Now, if you don't know who Srinivasa Ramanujan was, he was a great Indian mathematician. He was, I don't know exactly when he was born, probably in the late 1800s. And he was an astoundingly intuitive person who created wonderful results in a way that he himself didn't understand, often not proving them, just somehow magically coming up with them. And he wrote a letter, a very famous letter to G.H. Hardy, a great British mathematician, giving some of his results, and Hardy was just absolutely astounded by these results of Ramanujan and invited him to come to England, where they worked together for quite a long time. But unfortunately, Ramanujan, I think he contracted tuberculosis, and he eventually died of it. It was very tragic. When Ramanujan was sick, Hardy went to visit him in the hospital, and this is what is actually on the poster of Ramanujan Remembered. It shows a car, it shows a taxi driving along, and you can see the license plate of the taxi, and it's 1729. And so let me read you this little anecdote that Hardy related it. So he was going to see him when he was ill in the hospital. I remember once going to see him when he was lying ill at Putney. I had ridden in taxi cab number 1729 and remarked that the number seemed to me rather a dull one. Like I said, Bach's birthday, 238, that sounds sort of dull. Anyway, and that I hoped it was not an unfavorable omen. No, he replied, it is a very interesting number. It is the smallest number expressible as a sum of two cubes in two different ways. I asked him, naturally, whether he knew the answer to the corresponding problem for fourth powers. And he replied, after a moment's thought, that he could see no obvious example and thought that the first such number must be very large. So I want to comment a little bit about that. So I'll just write the number up here, and it's 1729, the sum of two cubes in two different ways. Well, if you happen to know that 9 cubed is 729, and if you happen to know that 10 cubed is 1,000, there's a sort of a self-evident fact here. This is 1,000 plus 729, which is 10 cubed plus 9 cubed. If you also happen to know the number of cubic inches in a cubic foot, which I do, which is 1728, 12 cubed, then it's 1728 plus 1, so that's 12 cubed plus 1 cubed. And so there we have it. It's the sum of two cubes in two different ways, and Ramanujan said immediately that it was the smallest number that is the sum of two cubes in two different ways. Now, what Hardy said, quite astonished by this little performance of Ramanujan's, he said, and you heard me emphasize the word naturally. He said, naturally, I asked him, what was the corresponding solution for fourth powers? Now, I just want to mention this word naturally, because it is natural. There are two aspects of it. I mean, one of them is that it's natural for a mathematician to want to generalize. That is, to take a given case and to see what is like it. What are things that are like it? What are related phenomena? In other words, to make an analogy, to do something in a different, slightly different framework. Instead of the framework of cubes, to do it in the framework of fourth powers. Now, I suspect, Hardy's a great mathematician. I'm a mediocre mathematician. My generalization was, let's go down to squares, not up to fourth powers. So, there are different answers for squares depending on whether you count 0 or not, or if you allow a square to be, like 9 plus 16 is 25 plus 0. Okay, that's two different, it's a sum of two squares in two different ways. If they have to be positive, then you can get 50, 49 plus 1, and 25 plus 25. And if they have to be different, all different, then it's 65. 65, which is 64 plus 1, and 49 plus 16. Okay, anyway, so that's an answer going downwards. What's that?
8 squared plus 1 squared.
8 squared plus... What did I say? That's what I said. I said 64 plus 1.
Oh, sorry.
And 49 plus 16. I didn't say 8 squared. I assumed everybody knows. 64. One of the aspects of the word naturally is that a mathematician is inclined to do this kind of generalization. That is, to make an analogy between this problem stated with third powers, and fourth powers, or second powers, or fifth powers, and so forth. But the thing is that if you really think about it, I mean, the statement is 1729 is, I hope is this too small? Yes? Well, I'll try to write it bigger, but I'll write it a little bit bigger. Smallest number expressible in two different ways as the sum of two cubes. Now, what's interesting is that there are a lot of things that Hardy could have varied. He varied only this. In other words, he didn't say, well, what's the smallest number that's expressible in 3 different ways as the sum of 2 cubes? Which is an interesting question. Or what's the smallest number that's expressible in 2 different ways as the sum of 3 cubes? Or what's the next smallest number instead of the smallest number? What's the second smallest number that's expressible in 2 different ways? And so forth. There are several loci of variability, so to speak. You can change that, you can change that, you can change that, and you can change that. But there's a sense of aesthetics going on here. And I think it's interesting that I think almost anybody in, I don't know how to phrase this, but a normal mathematical kind of a person would probably see this as the primary locus of variability. and would, with Hardy, ask the question for fourth powers or for nth powers in general. But they would also agree that these other things are perfectly valid and reasonable questions to ask, but maybe less tempting, less interesting. So there's a question of aesthetics here that is deeply lurking behind the scenes here, because Hardy didn't even mention the fact that he could have asked several other questions. He just said naturally asked about fourth powers. So I think it's a nice example of a very sort of simple analogy that just popped out of Hardy's mind instantaneously. Now, I might comment a little bit about fourth powers, because back in the, we have names for squares and cubes. They're called squares and cubes. But fourth power is called a fourth power, and we don't think about this very much. But it's not an accident. I mean, a square is a two-dimensional shape, and a cube is a three-dimensional shape. But a fourth power is something that we are not familiar with. We don't have 4 dimensions. We can't build an object that has 4 perpendicular dimensions or sides of the same length. And so back in the, I think it was the 1500s, when mathematics was sort of getting a re-beginning after having been sort of in a torpor for quite a long time, there was the main activity that sort of relaunched mathematics in Europe was the discovery of the formula for the solution to a cubic equation. Now, it was known ever since the Greeks, I think, that the correct formula for a quadratic, ax squared plus bx plus c equals 0, has roots minus b plus or minus the square root of b squared minus 4ac over 2a. I once was at a lecture where Andrew Wiles put up a transparency with this on it, and it was mistaken. He had the minus b not over the 2a, it was out in front. And some high school kid said, "Excuse me, Professor Wiles, isn't that a mistake?" And he said, "Oh, I guess my secretary made a mistake." So, I think this is the right formula. So here's a formula for the solution. For solutions, there are 2 solutions to a quadratic in general, that involves using the 3 coefficients of the polynomial in an expression, an algebraic expression that involves a square root. And I don't know exactly to whom it seemed that who made the analogy. I know that the first person to solve it was a man in Bologna named Scipione del Ferro, and he came up with a solution to actually a slightly simpler, well, you would think that the general equation is, the general cubic looks like that, ax cubed plus bx squared plus cx plus d. But if you just make this equation, x cubed plus px plus q equals 0. It's a slightly simpler equation. It still has the cubic term in it, but no quadratic term. Turns out that all cubics can be reduced to this form in a certain fashion, and I'm not going to go into that. But what's interesting about this, and what I think people today think is perfectly natural and obvious, is that it involves a cube root. This one here is a quadratic, and it involves a square root. And so you would think, well, naturally, a cubic equation is going to involve a cube root. So the actual solution is, if we take these p and q, it looks like this. It's a cube root of minus q over 2 plus the square root of q q over 2. I hope you can see this, squared plus p over 3 cubed. It doesn't matter very much, but just I'd like you to be able to see it. Plus a very similar expression where I write the same thing but a minus sign here. So minus q over 2 minus q over 2 squared plus p over 3 cubed. Okay, it's just a sum of two things. And indeed, it has a cube, well, it has actually what it's got 3 here. That's the crucial thing here is the cube. The 3 there is what makes the difference. These are cube roots. And so there is a clear analogy in a certain sense between this formula and this formula in that one of them involves a square root and one of them involves cube roots. But there's some differences. I mean, and in fact, one of the interesting differences is that there's a square root under the cube root. So it's actually a sort of a double root, a root of an expression that in itself is a root. So there's some hidden complexity here. Now, people were very intrigued by this. There are a lot of things I want to say about this. One of the questions was, we want to, well, I should say one other thing. The way that this was solved is by doing what is called completing the square. Completing the square involves making a sort of a geometrical diagram which looks like this, and where this is x. And I'm not going to go into the x being what we're looking for. I'm not going to go into all of the details of explaining how completing the square works. I just want to say that this particular diagram is the diagram that helps you solve the quadratic equation. And the way in which one of Scipione's rivals, Tartaglia, he wasn't actually a rival of Scipione because Scipione had died, unfortunately, but he was a rival of one of Scipione's students. Tartaglia generalized this idea, again, making an analogy to the analogous picture for a cube. And I think, if I'm not mistaken, I have the little objects here in my backpack. You can sort of see sort of distributed around here among my various clothes. Let's see. There's one piece missing here. One of the cubes. Well, let's not worry about it. Point is that it's sort of analogous. The analog to this square is this cube, and the analog to these two side pieces, these two wings that go around, are 3 rectangles that go around, that fit around in a very nice way, like that. And if you can see this well, you may not be able to. There's a little 1 by 1 cube here missing. I don't know why I say 1 by 1. It's some size. And it's not 1 by 1. It's 1 by 1 by 1. Whatever it is. So there's a little cube here missing. So what we have is that little missing cube is the analog of the little square up here. So there's a perfect analogy that was made by the solvers of the cubic equation. They took the same diagram and they just upped it a dimension. And were led to finding the formula for the solution to the so-called reduced or depressed cubic. Then there came the question of trying to solve the 4th degree equation. Now the 4th degree equation, ax to the 4th plus bx cubed, etc. Notice I say to the 4th, I don't say ax tesseract plus bx cubed or something, because there is no, or wasn't at that time anyway, there wasn't any 4th dimension. People couldn't imagine 4-dimensional things, and so the analogous diagram or structure or object was inconceivable to them. They couldn't generalize up one level. They couldn't make a physical picture that would be the same thing as this picture or as that structure. So actually though, it turns out the history is all very interesting, and I'm not going to go into it in any detail. But one of the figures involved, Ferrari, and also Cardano, who he was working with, the two of them, did solve the fourth degree equation. And they didn't do it using this method of using a diagram or a physical object. They managed to do it in some other way, and I don't remember. I haven't actually studied the details, so I couldn't tell you exactly how they did it. But anyway, they did, and they came up with an analogous solution again, in a certain sense. That is, it was radicals, that is, roots of things, nested downwards. But it was actually kind of surprising because there was no fourth root involved in it. There was no fourth root. You would expect that the quadratic is a square root, the cubic is a cube root. You would think that the fourth degree equation would have a fourth root in it. But no, it doesn't. Actually, it's, in a certain sense, it's simpler. In another sense, it's more complex. No pun intended. So the actual formula involves the highest root, the one that would correspond to this one, the analogous one to this one, the one on the top level, is a square root. Inside it, there are some other algebraic expressions, and there, among them, is another square root. And then inside that square root, there's a cube root. And then inside that cube root, there's a square root again. So it goes square root of cube root of square root. Not directly, because then you could just take the 24th root of something. But I mean, it's the square root of some expression, that part of which contains a square root, which is again of an expression which contains a cube root, etc. So 2, 2, 3, 2. So that was an interesting thing. It was a triumph. They succeeded in solving the equation, and in some sense the analogy worked. And if you say 2 times 2 is 4, the square root of a square root is sort of a fourth root in some vague sense. I mean, square root of an expression that has a square root in it, it sort of reminds you of taking the fourth root of something. So there sort of feels like there's something. And you get, there's something interesting going on, but it's clearly very elusive. And then the pursuit was made of the solutions to the quintic equation. Now, I'm going to briefly comment on I guess the crucial thing to do here is to point out that there's some interesting things in this formula for the cubic. A cubic equation, if you make a graph of it, some of them will go like this, and some of them will go like this. These ones have 3 real roots, and this one has 1 real root. I'm going to take an example of one that has 1 real root. So x cubed minus 15x minus 4 equals 0. This is one that was considered by the Italian mathematician Bombelli. And Bombelli plugged these things in here. So if this is q, if q is minus 4 and p is minus 15, if we then plug this in, you can try it yourself, I'm not going to work it out for you, but you'll just see that you get the square root of 2 plus the square root of minus 121 plus, did I say the square root? I meant the cube root. The cube root of 2 minus the square root of minus 21. Okay, so a cube root and a cube root. And now, the funny thing is, I don't know if you can see in the back, I wrote it a little small, but inside there's a square root of minus 121. Now, this equation was known to have 1 root. 1 root. What was that root? Well, it's 4, because try it. 4 cubed is 64. 15 times 4 is 60. 64 minus 60 is 4. Minus 4 is 0. So the root of this equation is 4. So here's a weird expression. Here's a very weird expression. It says the cube root of 2 plus the square root of a negative number. Now, I'm going to have to back off a little bit or go make a slight digression for a moment. It's very amazing. Firstly, they didn't even have equations in those days. There were no equal signs. They didn't have notation of any sort of this. They wrote things out in prose. And so to even imagine a solution like this was phenomenally difficult, let alone a solution to the fourth degree equation, which was much more complex. Cardano, who was the first person to publish these results, wrote a book called Ars Magna, which contained, 40 or some chapters devoted to the cubic and the fourth degree equation. And there were 13 chapters in the book devoted to the cubic. Now, why would there be 13 chapters when it's an expression that we can write down? I mean, this is the reduced cubic, but in any case, you can still write down the solution for a full cubic, the most general cubic possible, in one line. Why would there have to be 13 chapters? Well, the reason is that for Cardano and all mathematicians of his time, there were, the only numbers that existed were positive and zero. There was no such thing as a negative number. And so when you effectively, what it amounts to in modern notation is that all the coefficients of the polynomials had to be positive. So there would be one case, you would have to transpose this. You would have to say x, okay, here's a different case, x cubed equals 15x plus 4. You put them on the other side. And then you say, for equations of this form, I have a certain solution. And then if this were a plus 4, then that would stay on this side. You say, I have a different solution, although closely related, for equations of this form. And there were 13 different sets of equations. And all of this because they did not recognize the existence of negative numbers. So already, negative numbers were a big breakthrough. The idea of being able to extend numbers, extend the notion of numbers beyond the positive to negative was a deep mathematical breakthrough that took place only a few hundred years ago. Only minus 400 years in the future. So once they were welcomed into the club of numbers, it was still known. I mean, it took clever people to figure out the rules to multiply negative numbers into positive numbers. But they did figure them out. And actually, I think, I may be wrong on this. Maybe Marcello, can you tell me if I'm wrong? Maybe you know. Where are you? Back there. I don't know if Bombelli was the first person to formulate the rules for multiplication of positive and negative numbers.
I think so.
Yeah, I think so too. And so Bombelli in Bologna formulated the rules for multiplying, and a minus times a minus is a plus, and a plus times a plus is a plus. So nothing, no known number multiplied by itself ever gives you a negative number, because negative numbers squared give you positive, and positive numbers squared give you positive. So there is no such thing as the square root of minus 121. And yet here it was occurring in their formula. Not only that, very annoyingly, it was equal to 4 theoretically. This thing had to be equal to 4. That's really bizarre because, I mean, here are these two different, the same expression, but used in two different ways, and yet it's a nonsensical, bizarre expression. And yet, what's interesting is that Bombelli was able to cube this number, because you can call this just a plus b. And if you actually just, you can just do it yourself on a piece of paper. If you just cube a plus b, cube this and cube this, well, of course, the first thing that happens is that you get the cube of this term, and so you get just 2 plus the square root of minus 121, and then you have the cube of this term, but then you have some cross terms. But the cross terms actually turn out not to be a problem, and it turns out that you get exactly 4. everything cancels that needs to cancel, and you wind up with, when I said 4, what I mean is, I didn't say it right. What I should have said is, because there are two uses of 4 in this discussion. One is that this is supposed to be equal to 4, and there's this other 4 here, which is different. But so what I'm trying to say is that if you take x cubed minus 15x, if you just calculate that, that should be equal to 4, and by God it is. Because of cancellations and nice things. So in other words, this one cancels that one, because when you cube the two of them, this one, they come out, this cube root comes away, and this cube root comes away, and you have a 2 here, plus a 2, which is the 4, and then you have those things that go cancel each other. And other things happen with the cross terms that make it work out very nicely. I'm not going to go into the details. So, in fact, Bombelli was using this number, this expression, as if it denoted a number, but he didn't have any idea what it was. And eventually, with his work and the work of successors, these strange objects started getting incorporated into mathematics. And they were incorporated because they sort of behaved the way other numbers behaved, but it was a very daring extension, assuming that these numbers would behave like their cousins. And I just want to take a simpler example of this same kind of phenomenon, to show the ubiquity of analogy in mathematics. I want to just take a very simple example that probably everybody here knows, which is just the definition of the power of a number. So if we have a to at the nth power, we know that means n copies of a multiplied together. So if it's 3, it's a times a times a. And if it's 2, it's a times a. And if it's 5, it's 5 of them. And of course, there are 2 there, and there are 3 there, and so this is a cubed, and this is a squared. And we sort of see an obvious rule here, which is that if we put a to the n power and multiply a to the m power, we get a to the n plus m power. Now, that's probably something you're all familiar with, very familiar with, and it seems like a triviality, a tautology in a sense. We're just counting how many a's are being multiplied. The thing is that it also, though, will allow you to make some daring generalizations if you say, well, I'm interested in taking this as the basis for my understanding of what powers will do when we're not talking about positive integers. I mean, just for example, if we take m to be 0, we have then the general rule of a to the m times a to the 0 is going to be a to the n plus 0, but n plus 0 is n, so that's a to the n. And look, we have a to the n times something equals a to the n, so this thing has to be 1. So that's, we've come up with the idea that when we multiply a by itself 0 times, what do we get? 1. So that's an interesting sort of analogical generalization. We've said that we're going to make this formula work in areas that it hasn't been used. We have no proof for it. We're just going to define things to work this way. So then the next thing would be to say, oh look, a to the n times a to the minus n would have to be a to the n minus n, because n plus minus n is n minus n, and that's a to the 0, which is now, we know, 1. So that tells us that these two things are each other's reciprocal. So a to the minus n equals 1 over a to the n. So now we have now we know how, or I'm not saying we know how, because this is, we are going out on a sort of leap of the imagination. We're more saying, if these things act like their cousins in the way that we would like, if they obey the same rule, which we think of as being a very elegant rule, we would like it to be obeyed, then we would have to have this to be the case. So we're using this idea of generalizing something by analogy into a domain where it has never been done before, never has existed before. And then, of course, we come to more interesting cases. We can say, what is a to the half times a to the 1/2? Well, that's got to be a to the 1/2 plus a half, which is a to the 1. I'll just leave the 1 off. So that means that this thing times itself is a, which means that this thing would have to be the square root of a. And so then we can similarly see a to the 1 over n is going to be the nth root of a. And so forth. So we get all sorts of, we reap all sorts of wonderful things from using this equation as a springboard and generalizing. These are ways in which mathematicians generalize naturally. Okay. Now, I wanted to say very, very brief words about the pursuit for the 5th degree equation. The 5th degree wasn't solvable by Cardano or by anybody else at that time. Lots and lots of people pursued it for another couple of hundred years, and nobody was able to find a solution using a 5th root or any other kind of roots. And it was, everybody felt that it had to be solvable, but nobody could find the solution. But there were people exploring all sorts of pathways. And it's interesting that so many of the pioneers were Italians. The first person who really understood that this was not going to be doable was named Ruffini, and he published a proof that it was not doable in 1799. Unfortunately, there were some small gaps in the proof, and a lot of people didn't believe it because it was such a well, I shouldn't say radical. It was such a bizarrely unexpected result that they were reluctant to accept this result. There were people who believed him. Cauchy, for example, in France, was a supporter, I'm glad to say. But because I feel that Ruffini deserves a lot of credit for this very heroic act that he made. I might also mention, curiously enough, while we're speaking about analogies, that Ruffini's proof was based on the symmetries of roots, which I'll go into just very briefly in a moment. And he decided that he was actually, I think he was a medical doctor, and he was interested in the nature of the human, I don't know what the word is exactly, but sort of the human soul or psyche or something like that. And he decided to use his proof to prove that this soul that was immaterial. And he managed to convert his entire proof, step by step, of the unsolvability of the quintic into a proof of the immateriality of the human soul. I was just absolutely blown away when I first read about this. It involves certain kinds of assumptions, needless to say. It's funny how you can never predict what word is going to make people laugh. I mean, how can the word assumption make people laugh? But I guess it does. Anyway, that's sort of beside the point. But it is interesting that he made this very detailed analogy between two different different domains. What I wanted to say, though, is that back in that time, in the late 1700s, early 1800s, people were starting to understand that what mattered about the roots of equations was the way they behaved. I mean, that may sound stupid, but let me show you what I mean. Let's take I, the number I, which we now accept as being the square root of -1 without even thinking about it, without paying attention to the heroic daring of people like Bombelli and successors who played with it, even though they had no idea what it was. Even people many, 100 years, 200, 300 years later were dubious about it. So I is this ethereal thing whose square is -1. It's not a negative number, it's not a positive number, it just sort of floats out there. But we can do things with it. We can multiply it by 2, we can take half of it, we can add it to 5, we can do all sorts of things with it. One of the things we can do is we can take -I. So I'm going to call that J. J is -I. Okay, now I and J are basically, they act indistinguishably from each other. What do I mean by that? Well, each of them, 1 squared, is 1. Because I squared is 1, and since J is -I, it's going to be, when you square it, the 2 minuses will cancel each other, and it'll just be left with I squared, which is -1. So J squared and I squared are the same thing. So how can you tell which one is which? Maybe we labeled the wrong one I. Maybe actually we should have called the other one I. Does that make sense? Maybe we actually have been fooled the whole time. We've been calling I, J, and J, I. Doesn't make sense, does it? You're laughing. You're laughing. But you understand that this makes no sense because they're indistinguishable. And yet they're distinguishable because they're not the same thing. Because they aren't the same thing. If they were the same thing, then I squared would be the same thing as IJ, but IJ is +1. And I squared is -1. So they're not the same thing. They're different things, but we can't tell them apart. They're like Tweedledee and Tweedledum. Okay, we can't tell which one is which. Let me now go and show you the spirit of this idea in a different context, the context of a more familiar one. This equation, the one I was just talking about is this equation. This equation has the roots I and J. This equation, x squared minus 2 equals 0, has 2 roots. It has the root square root of 2 and minus the square root of 2. They're familiar to you. One is 1.414, etc. And the other is minus 1.414, etc. Now you know those aren't the same number. And you know where they are on the number line. One of them is to the left of 0 and one of them is to the right. So they're not the same thing and they're very different from each other. And yet they behave identically in a certain sense. In a certain sense, they're indistinguishable from each other. Now, what do I mean by that? What I mean by indistinguishable is that if you don't know their magnitudes, if you say, oh, here I have the rational numbers, not the reals, just the rationals. I take all the rationals, and I say, look, there's no square root of 2 among them. So I'm going to add a mysterious quantity to the rational numbers. I'm going to call it, I don't know, I'll call it S for square root, and I'll call this one T. And S and T are each other's negations, or, one is minus the other. But I don't know that they're on a real line, because I'm not thinking of it in that sense. I'm just thinking of it as a mysterious, magical quantity whose square is 2. Because I only know rational numbers, and there isn't any rational number whose square is 2. So I just say it's a mysterious quantity. I don't know its magnitude. It has no magnitude. It's just a quantity that obeys the equation s squared equals 2. And this one is also st squared equals 2. And s plus t equals 0. That's all I know. Now if I know that, then these two quantities are indistinguishable algebraically. And I could go into more detail, but I'm not going to. I just want to give you the flavor of this to say that back in those days, people were starting to think about the roots of polynomial equations in this way. That is, instead of thinking about them as located on the number line, somewhere on the real line, or in the complex plane for that matter, they were thinking of them as mysterious, magical things that had only one property, basically, other than obeying the laws of arithmetic. That is, you can multiplication is commutative, addition is commutative, and so forth. Multiplication distributes over addition, things like that. but they
Didn't have magnitude.
replace one by the other, and nothing would appear to have changed. It would be like looking at something something that's mirror symmetric in a mirror. Nothing would change. In the case of I going to minus I, that's called complex conjugation, or I going to j if you want to call it that. And you can't tell if you've exchanged I and j. There's no way of knowing. Similarly, there's no way of knowing really whether s is the name of the square root of 2 or s is the name of minus the square root of 2, because we don't know which one is, we don't have magnitudes attached to them. So we can't say s is 1.414. No, s is not a number of that sort. S is just the thing whose square is 2. So, one of the two things whose square is 2. So, what about cubic equations? Well, cubic equations have 3 solutions, and so the complexity of the symmetry is a little bit greater. Instead of exchanging two things, you can make them kind of cyclically permute. So you have 3 solutions, s, t, and u. S goes to t, t goes to u, and u goes to s. And you can make cyclic permutations of them. Or you can interchange s and t alone while u stays fixed. And all of these things are going to leave a certain quality of the equation or of the number system untouched. You're not going to be able to tell that you have done these operations. Now, without going into any detail, I'll simply say that this idea of making substitutions, as they were called, that is, cyclic permutations or swapping two things, was invented in the late 1700s by Lagrange and studied very deeply by Ruffini, and studied also then by Abel, and then studied by Galois. And what these people came up with was a very abstract thing called the theory of groups, which I don't have any time to explain to you, unfortunately. And the theory of groups was treating these substitutions as if they were a certain kind of number. Now that may sound extremely weird to you, but what I mean is that you could, for example, if you took your, let's say, st and u, and you did a cyclic permutation, you could do the cyclic permutation again, and it would give you s, instead of going s goes to t, then it would go s goes to t and t goes to u, so s would go all the way to u. And u would go to t, and anyway, it doesn't, I'm not going into detail, but the idea is that you could square the permutation, the cyclic permutation, or you could cube it, and in which case then you would just get no result at all, because s would go to t, it would go to u, go back to s. So if you could cube up one of these substitutions, you would get back to the no-op, which is like getting back to 1, multiplying by 1. And so this was kind of like multiplication. It was kind of a very abstract analog to multiplication. And so these substitutions generated tables of multiplication. You studied the interrelationships of substitutions, and you got tables that were like multiplication tables. And you could study the patterns in these multiplication tables and deduce things about the equations whose roots were being manipulated. And that's a long story, so I'm not going to tell it. But what I'm saying is that the crucial thing here is that these new things, so-called substitutions, were acting like numbers because we had multiplication tables for them. So we had generalized the notion of number in a very abstract way. Moreover, now these things, the multiplication tables were this set of all the substitutions for a particular equation was called a group. Galois gave it that name. A group of substitutions. And there could be subgroups inside a group. And then, here I'm going to get very abstract, but only for a very brief moment, because then I'm going to go off into much more tangible things. But all I want to say is the group could be seen, the table of multiplication, I'll just write it out to show you the idea. The multiplication table, as you know, is a sort of a square. And so if you have 6 elements in the substitution group for a cubic equation, it's going to be a 6 by 6 matrix. That is, the multiplication table is going to have each of the substitutions up here. I'll give them names. Just like an ordinary multiplication table. Of course, the ordinary one would be infinite, but this one is finite. But anyway, here is this multiplication table, and it's got, you know, I times I is I, and P times Q is I, and P squared is Q. And anyway, it doesn't matter how it's filled out in some fashion or other. This is the multiplication table for this group of substitutions. Each of these items here is a substitution, meaning either a cyclic permutation or a swap or nothing at all. Well, this multiplication table turns out to have only P's and Q's up in here and down here, and only F's, G's, and H's in this area and in this area. And so it has a certain structure. And Galois looked at this. I mean, he didn't look at it exactly when I'm drawing it, but in his mind he looked at it, and he said, this sort of looks like I'm dividing this 6-element group by a 3-element group, which is the group of I, P, and Q. I'm taking the 6-element group, and I'm sort of equating I, P, and Q, and I'm sort of considering them as a unit. So I see what I'm left with is just a thing that looks like this. And this is the multiplication table for a simpler group. And so he says, I divided a big group by a little group, and I got another group. And so what is really going on here is something phenomenally abstract. Now, we already said substitutions were a kind of weird generalization of numbers. Now we have substitutions all taken together as forming a group, and now we're taking groups as if they were the whole group as if it were a number, and talking about dividing one group by another. It's a phenomenal generalization of the notion of division, an incredible abstraction, an incredible analogy, an incredible leap of the human mind. And if you ever have a chance to study Galois theory, you'll understand what I'm talking about. Group theory by itself already is basically, you don't need to study all of Galois theory to understand these ideas, just group theory. So all I'm trying to say, though, is that without giving you a very clear understanding of what these things are, I'm just saying that mathematicians began with this notion of division, at, say, for example, or multiplication, and they generalized it in such unbelievable ways. And this, mind you, is all taking place about 200 and some years ago. The generalizations that have gone on since then are, as I say, so mind-boggling that they leave me completely in the dust. I'm already mind-boggled by what Galois did when he was 17 years old in 1827, let alone by what people have done in the next 100 and nearly 200 years. Okay, I think everybody's caught on. You like patterns. Mathematicians like patterns. What's going on here? He says in his book, find a simple proof. So I sat down and thought about it for a while. And I did. I found a couple of simple proofs. One was simpler than the other. And it was interesting to me because I showed them both to my son, who is not a very math-loving person. And he was very kind to me. He said, the second one, è più semplice ma è meno bello. It's simpler, but it's not as pretty. Now, can you imagine a kid who doesn't like math saying, this one is simpler, but it's less pretty. But è sempre bello, ma meno bello. It's still beautiful, but not as beautiful. Now, this is a non-math kid. Non-math. And he's calling these things beautiful. So I was thrilled that he would do it. Now I want to talk to you, I'm going to show you the simpler proof, the less beautiful proof, okay? You may already have thought about it. I'm going to tell you how I got there. All right? How did I get there? Well, if you look at these equations, one thing you're struck by is, of course, that they're increasing in length, right? I mean, that's clear. Another thing you're struck by is that this is 2, 1, 3, 2, 4, 3. I mean, this side is always one thing short. Or another way of putting it, this is 3 elements, this has 5 elements, this has 7 elements. We're going to have the odd numbers. And if you look carefully, there's something, I don't know how to say it, but that draws your attention to these numbers here. Maybe it didn't, but notice that 15 is the last one here. So this first one is going to be 16 plus 17 plus 18 plus 19 plus 20 equals 21 plus 22 plus 23 plus 24. Okay, so we got the next square. So we seem to be going down square with squares. So what does that do? It sort of separates this element out. It sort of says this element is a little bit different, which is kind of nice because then it makes everything sort of go pairwise. It sort of says, look, maybe there's a kind of a connection between this and this, and maybe there's a connection between this and this, and maybe there's a connection between this and this. I don't know, maybe I'm just guessing. But then I think to myself, what if I just move these over to the other side? I say, okay, so 9 equals 13 minus 10, plus 14 minus 11, plus 15 minus 12. Why not? Let's try that. Hey, this is 3, and this is 3, and this is 3, and 9 is 3 times 3. Maybe that's just all that's happening. Maybe I'm just saying that 3 times 3 is 3 plus 3 plus 3. That's really all it's saying. And that's what's happening. So we do the same thing here. 21 minus 17, 22 minus 18, 23 minus 19, 24 minus 20. 4 plus 4 plus 4 plus 4. So what we see is analogies galore. Firstly, there's sort of the analogy that we find that connects all the squares. And there are many other analogies here. I mean, there's the lines that connect all these, the analogy that connects this line to this, this to this, this to this. All of those are analogies. But there's the analogies of these things all being connected to each other, 1 squared, 2 squared, 3 squared, 4 squared. There is then the kind of implicit hazy mapping that says maybe this is connected to that. Maybe this is sort of an analogical hint. Maybe those are connected. And then you pull them over and then you get it. And then the proof works for each line. So this is just an example of how analogy sort of pervades mathematical thought at a very concrete level, but in a very pretty way. I think this is a very pretty proof. The other proof may even be prettier. I don't know, but it's a little bit more complex. Now, finally, I'm going to come to a conclusion with a little discussion of some things that I myself explored when I was an undergraduate in mathematics at Stanford many years ago. And in order to explain that, I probably should say, to set the stage, that I'd had an exchange with a boy who was a little older than me, who was also very talented at math. In fact, he's a member of the math department at Princeton now. Or maybe he's retired for all I know, anyway. And he became a very distinguished mathematician. And he and I were friends, mostly pen pals, but anyway, we were sort of friends. And he set a problem for me, which involved what I will simply say are the differences between two triangular numbers. Now, here is a picture of some cannonballs, you might say, or I don't know what you want to call them. But anyway, here's a triangle made out of circles. And how many circles are there? There are 5, 4, 3, 2, 1. So 5, 4, 3, 2, 1, that's 15. And if I have just taken this part of it, it would be 10. And this part of it would be 6. And this part of it would be 3. And this part of it would be 1. So the triangular numbers are the sums of consecutive integers. 1, 1 plus 2, 1 plus 2 plus 3, etc. And here they are written backwards. 1, 3, 6, 10, 15, 21, and so forth. And he had asked me, questions about the differences of triangular numbers. What numbers can be represented as the differences of triangular numbers? Well, I just want to simply, how to say this, point out that this is a typical mathematician's question, that takes two things that are, I mean, triangular numbers are just sort of a thing, and it throws in another concept, differences. And it says, let's explore what happens when we combine the notion of triangular numbers with the notion of differences between them. It's sort of like, let's see what happens. This is mathematical game playing, but this is what mathematicians do. So this was the question he asked me, and I managed to solve it. But I got interested in it in then asking other questions. Again, by analogy, I said, well, now that I've solved the differences, let me do the sums. How about the sums of triangular numbers immediately? That was my first thought. It was a difficult question, and I wasn't able to solve it. And so I wound up doing something that was almost just playful. I don't know why I did it, even. But I took the triangular numbers, so I'm going to write them out here. 1, 3, let me see how I'm going to do this. Yeah, I guess this will do. 1, 3, 6, 10, 15, 21, 28, 36. That's plus 8, plus 9, plus 10, plus 11, plus 12. Okay, we get the idea. And I don't know why. I started looking at the triangular numbers and the squares. I mean, triangles and squares, you know, why not? So, and I put 1 here, then 4 goes here, then 9 goes here, then 16 goes here, then 25 goes here, 36 coincides. That's 6 squared, 7 squared, 8 squared, 9 squared, and so forth. Now, for reasons that I'm not going to explain, I sort of drew a line here. Oh, sorry. Here to the left of each square. Something like that. And then I counted how many. No, I did it. Well, let's see. I guess I did it the other way around. I put it to the right of each square. I'm sorry. I must have put it to the right of each square because this isn't giving me the thing that I wanted. I don't know. I'd have to. I should have prepared this a little bit. So let's try it again. Maybe this time it'll work. So if I draw to the right of each square, okay. Okay, now let's see what this gives me. Well, I'm not getting what I wanted. I don't know. Did I make a mistake here somehow? The point is that I should be getting 2 in here, and I'm getting 1 in here. Maybe, again, I should have put this to the left. I'm confused, because I should be getting 2 here, 1 here, 2 here, 1 here, and I should be getting 1 here. So this should have been to the left. I don't know what's going on. I'm not going to worry about it, because you can do it at home. I must have made some little glitch here. But the point is that I got a sequence of 2s and 1s. That's all I'm saying. I just started exploring it for no reason at all. And I got this sequence of 2s and 1s. And I can give it to you exactly. And there's no fussing around. I mean, there's no trickery involved here. I don't know why I'm having any trouble at all here, but I'm not going to pause to try to figure it out. The point is that I got this sequence of 2s and 1s, which look like this. And so forth. And I couldn't see exactly what pattern it had, but it was very interesting to me. First of all, it was interesting it was consisted only of 1s and 2s. Secondly, it was interesting that it seemed to be consist only of 21s and 2 11s, you might say. Even though 211 had nothing to do with it, it was just a 2 and a 1 and a 1, but visually it looked like that. And so, I explored this for a long time, and since the 2 11s were sort of rarer, I circled them. And I was looking at this for a while, and I noticed something that was interesting. I noticed that there were 4 terms in here, and then there were 2 terms in here, and then there were 4 terms in here, and then there were 2 terms in here, and so forth. And it took me a while to think carefully, but finally, after a while, something inside my head clicked, and I took half of this. And it was 2, 1, 2, 1, and it turned out that this sequence was the same as that sequence. And I was just completely bowled over. This was when I was about 16. It was about my 16th birthday or so. And it was just a phenomenal experience to have this magical thing happen, that this sequence that I generated, just playing around with triangular numbers and squares, has suddenly given me this bizarre self-involved property. That if I wanted to know how many 21s were between 2 11s, it was the same as the sequence itself. Well, I was hooked. Now, what did I do? Being an avid disciple of Hardy, I did the natural thing. What is the natural thing? I said, well, I took triangular numbers and I took squares. So what should I next take? Pentagonal numbers. And indeed, they do exist, such things as pentagonal numbers. I mean, squares look, they look like squares, and I just drew a triangle for you. Pentagonal numbers look like pentagons, and I can draw it for you if you want, very briefly. I'm not going to spend any time on it, but basically, the first one is 1. Then you draw a pentagon, a regular pentagon. The second one is 5, needless to say. And then the third one let's see, how does this work? I didn't do this very well. Anyway, something like that. Okay, if you count them, it should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did I leave something? Did I do something wrong? I'm screwing up here. It should be 12, and it's not 12. 1, 2, 3. What? I can't hear you. It is 12? 6, 7, 8, 9, 10.
Middle.
I'm not counting these. Oh, maybe I should be. Okay, 12. All right. 1, 5, 12, 22, etc. Yes, I should have been. Of course I should have been. I wasn't thinking. All right, so pentagonal numbers exist, and I can put squares in between them, or I can put triangles in between them, and I can start seeing what will happen. And so indeed, I got new sequences out that were interesting, but they didn't have quite the same properties. So I was led to thinking, well, I haven't gotten as much joy out of this exploration as I wanted. I got some joy, I found some new sequences, but I can't understand them. They don't have the same properties, the same magical self-giving back properties as the things that I found with triangles between squares. So I said, let me just go out further on a limb, even further. So I said, okay, what the hell? I'll try powers of 2 and powers of 3. So, again, I'm not going to, 1, 2, 4, 8, 16, 32, and so forth, versus 1, 3, 9, 27, 81, there's 64, and so forth. And once again, I got a sequence that consisted of only 1s and 2s. And I was very happy, and I could count, in fact, the 1s in between 2s. And again, I got another sequence that consisted of 1s between 2s. And again, I could count the 1s between 2s and that. And I got another sequence that consisted of 1s and 2s. And it went on like that. But eventually, it turned out I got a sequence that consisted of 2s and 3s. And then, or 3s and 4s maybe it was. And whatever it was, I would always get a sequence that consisted of 2 integers. No matter how I would take the original sequence and count things between it. That would give me a new sequence. And I would count things in that. That would give me another sequence. I called this taking a derivative. And I seem to be able to take the derivative infinitely many times. And I love this. And I found a formula for this. It was a very simple formula. It was very easy to solve the equation. And I'll write it down. It was that the kth term, and I called it the eta sequence, an eta sequence. This eta sequence, the kth term of this eta sequence looked like this. Log 2 to the base 3 Now, the brackets mean the greatest integer contained in. In other words, log 2 to the base 3 is about, 1.4 or something like that. So if I want the 5th term, I take 5 times 1.4, greatest integer in it, minus 4 times 1.4, greatest integer in that. And it's a difference between 2 integers. So I'll get an integer, and it always turns out to be either 1 or 2. So very nice. This was my formula, and I took it into my favorite math professor at Stanford, Gordon Latta, and I said, I have this really neat thing that I've found. By counting powers of 2 between powers of 3, look at this nice formula and look at these nice sequences that I get. And I said, I want to generalize this. So I have a neat way of generalizing it. I'll change 2 and 3 to n and m. And Gordon Latta looked at it and he said, Doug, why don't you just replace log n of m by alpha, any real number? And I was flabbergasted. It was so simple and so natural a thing to do. But I want you to think about this. I just want you to put yourself in the position of little me. I mean, I was 17 or 18, or maybe I was still 16. Anyway, I was a teenager, and Latta was in his 30s maybe. It's interesting how we saw it differently. For Latta, the generalization of log 2 to log to the base 2 of 3 was just any real number. For me, the generalization was log to the base n of m. Now, if you actually think about it carefully, I won't bore you, but you can approximate any real number by taking 2 integers. I mean, whatever number you want, you can find 2 integers such that this is arbitrarily close to any real number you want. You want it to be close to pi plus 10? Well, you can find an n and m, it'll give it. But I wasn't thinking along those lines. I wasn't thinking about that fact. I was just thinking that the natural generalization of this is as 2 loci of variability, and they're both integers. And he had this other vision of it. He said, this has nothing to do with logarithms. This has something to do with just a general idea that you have a real parameter in here. Just do it. And that was a big, big breakthrough for me. Because once I released myself from the bondage of, see, I had been thinking about counting powers of n in amongst the powers of m. That's it all came from where I had come from. I'd come from counting powers of one integer between powers of another integer. So for me, this sequence was tied to its origin. That's all I could see. For Gordon, it was just a formula. It had nothing to do with its origin. And he was able to completely abstract away the origin and to see it much more objectively. Once he replaced this thing by alpha, then a whole new world was opened up to me. And I studied these sequences. Now I can put a parameter alpha in here. I studied these sequences for many years, and I found millions of properties of them, and I'm not going to go into detail. It turned out I wasn't the inventor of them. They had been invented before by Christoffel and also by one of the Markovs. So, but nonetheless, I found all sorts of things that nobody else had ever found. I wasn't the first inventor or discoverer thereof, but I was able, to find things that nobody else had found. Anyway, to conclude, I will just simply say that that when I hit my abstraction ceiling in graduate school in Berkeley, maybe I'll say one other thing before I go to graduate school. While I was doing this several-year exploration of number theory using computers and proofs and friends and so forth, I was absolutely exhilarated and intoxicated. It was, in a certain sense, the most intellectually exciting period of my life, because I just can't remember ever being so excited by the ideas that they were just pouring out of me, one after another, after another, after another. And this was when I was an undergraduate at Stanford, and when I went to see Gordon Latta, he loved them, these ideas. But there was another mathematician in the department, and thank God I don't remember who it was, but I went and talked with him one day, and he said, "This isn't even mathematics. This is not even mathematics." And what I suppose he meant was something along the lines of, today we do things that are hyper-abstract. We make Galois look like, we do Everest compared to Galois' foothills. And this is not in the foothills. This is like, playing in the mud. And so this is not mathematics. I was, hurt, but at the same time I had a certain degree of self-confidence. But I was confused. I was confused that one person would like it and another person would think it was contemptible. So it was a weird feeling for me, and I found out in graduate school, in any case, I went to Berkeley, that this kind of thing was not very popular. That it would at best have been considered sort of 19th century math, and and I wasn't going to become a great mathematician, no matter how much I was intoxicated by this stuff. It wasn't going to lead me down the pathway to becoming a great mathematician. And I wound up dropping out of graduate school in math. But I didn't know what to do, so I thought about it for quite a long time. And eventually, as Raphael said, I wound up getting a PhD in physics, doing something which was the study of some stuff. Why do you laugh at the word stuff? I'll have to remember to say that in my next lecture. And also, what was the other word? Assumptions? Okay, I'll remember those two words. Next lecture, I'll make sure I say those words. So I was, in graduate school, I had a prejudice, which was in physics, which was the only good thing in physics is particle physics. No, there's one other good thing. It would be cosmology and general relativity. Either you go to the littlest or you go to the biggest, but nothing in between. And solid-state physics, that's engineering. That's not even physics, to paraphrase a certain mathematician. And yet, I won't go into details. I had a lot of trouble in particle physics. I couldn't hack electrons in magnetic fields, and instead it was a very weird problem because it had to do with things that normally never come up in physics. That is, magnetic fields, which, if measured in a certain way, have either a rational or an irrational value. And I had been, in my study of eta sequences, the difference between rationals and irrationals was fantastically important. And so I had a lot of experience with thinking about rationals and irrationals. And I thought, this is funny. Here's a professor who's talking about rationals and irrationals. And I have some sort of dim experience back 10 years ago with these things. Maybe I should just, what the hell, go into this part of physics. Solid-state physics, I cringe. I can't stand it. But I'll hold my nose, and maybe I can get a PhD. And so it turned out that the work that I did in that branch of physics was I can't explain it, it's too long. So all I can say is that I wound up in 1974 doing some computer work that generated a graph that looked astoundingly like something that I had already discovered back when I was doing eta sequences. I called it the int graph, and I don't have the time to explain it. But I had found the int graph in about 1963, and I had studied the hell out of it, and I understood it backwards and forwards and upside down. And it was a graph that was consisted of infinitely many pieces of different sizes, each one of which was exactly a copy of the full graph, except slightly distorted. And when I was trying to solve the spectrum of the electrons in the magnetic field, it turns out that the graph that I generated by computer, by the way, no physicist would dare use a computer then. Dare isn't the right word. Deign is the right word. No physicist would deign to use a computer back then. They were all into doing the mathematics, formally. They had to do it with formal manipulations. I was too simple for that. I could only do it by computer. So I created the visual structure that I looked at and I recognized. I said, hey, I've seen this before, or something awfully like it. And because of my experience with int, I was able to make a huge number of analogies and to understand this graph that the computer was giving me in a way that none of the physicists had any inkling of. I had the right background. I had all the material to make the right analogy, and I understood this graph, which I called G-plot, and which later came to be called Hofstadter butterfly. Maybe I can open it and see if I can show it to you. Yeah, there it is. Is it somewhere? Yes. You can't see it very well, but anyway, it doesn't matter. That's the graph that I studied, and it consists of infinitely many copies of itself at different sizes, distorted. And it was just what I had studied, well, not this graph itself, but similar graphs, when I was an undergraduate studying the eta sequences. So the weird thing is that I wound up getting a PhD in physics doing the number theory that I had thought was so intoxicating, and which some mathematicians thought wasn't even mathematics. And I wound up getting a good PhD, in fact, a very, very good PhD. It became a very famous thing. I was just lucky. I was extremely lucky that I was able to do this. So anyway, I hope to have shown you some of the role of analogy in mathematics. And if there's any time, there's probably a negative amount of time left, or an imaginary amount of time. If there is any time, I'll be happy to answer questions. Thank you.
Thank you very much for a wonderful lecture. I think we do have time to take some questions, and I would suggest that if you do want to ask a question, either really speak up, or maybe even better, come up here and pose your question.
I saw somebody else back over there too, so. Unless you can talk really loud.
Thank you very much for talking. I was wondering, both the title of your talk and just what you just said about your butterfly reminded me of...
Can you speak into the mic?
Oh, am I speaking to the mic? I can't. Is this the mic? Okay, sorry. There. Okay, so it reminded me of, I think it's Wigner famously said that it's a miracle that mathematics is so useful in physics. But I always think that it isn't, the miracle is really that analogy is so useful in mathematics. And the real amazing thing is that you can make these, I mean, and that, since you wouldn't expect different parts of mathematics to be related to each other because they're set at different times and places and to be free creations, and yet there are all these weird analogies to be had. And I wondered if you, do you think that that's related?
Well,
The way we use, the way we're successful in physics is related to the way we're successful in drawing analogies in mathematics, pure mathematics itself.
yeah, I see the question. I mean, the title of Wigner's article was on the unreasonable effectiveness of mathematics and physics, I think. Was it?
I think so, yeah.
Something like, or in the physical sciences, something like that. It was, and you're saying on the unreasonable effectiveness of analogy in mathematics.
Or the unreasonable effectiveness of mathematics in mathematics. Because it's two different parts of mathematics, you know.
Yeah, why would one field, yeah. It's a very interesting question, and I guess it's too hard for me to really give much of an answer. Brains are built, it makes us select out certain things and find connections. But why those connections work very often? Well, very often they don't work. I mean, that's important. I had an example in my notes that I was going to show you of an analogy that didn't lead anywhere. I can mention it very briefly. You know, triangles between squares, I was counting, triangles are 1 plus 2 plus 3 plus 4 and so forth. And squares, in case you don't know it, are the sums of consecutive odd numbers. 1 plus 3 plus 5 plus 7. You've sort of had a hint of that already today. I said, well, what if I just change the pluses into timeses? What if I take the factorials, 1 times 2 times 3 times 4, etc., and count them between products of odd numbers, 1 times 3 times 5 times 7, and so forth. And I generated all these products of successive odd numbers and all these factorials, and I counted between, and I got some interesting things, but it didn't lead anywhere. In other words, it was an analogy, and it was a neat analogy. It started out well, but it sort of fizzled. And so what happens in such a case? You just drop it. You don't publish an article saying, here's some stuff that I don't know anything about. I mean, you drop it. And when you find something that works, you publish it. So in a certain sense, the unreasonable effectiveness is because you're a censor. You censored all the ones that didn't work, and you published the ones that did work. So I don't know.
Thank you very much.
Yeah. Well, wait, there was...
Yeah.
Okay, and then
so follow up, I think, on the previous question. So you talk about the effectiveness of mathematics in describing the physical world, right? My question is, why have we not discovered, or why we have not invented the mathematics that would is as effective in dealing with, say, human interactions, human emotions, motivations, and so forth? You think about in terms of phenomenology. We, humans interact with each other and we talk about personality, talk about emotion, feelings, and so forth, as we observe the stars, the galaxies, and so forth, right? So when we imagine that you have some pattern that you recognize, then you can crystallize, use some kind of mathematics.
Well, I can give you an answer. I mean, obviously it's a complex question, but I think that the answer isn't actually all that difficult. I mean, the things that physicists have studied have been extremely simple things. I mean, even back in the days of classical physics, which in a certain sense was very simple, it was all sort of frictionless worlds. Things were moving in a vacuum under very simple kinds of forces. You study the most simple possible systems, and it's not surprising they obey simple mathematical laws. And then when you come to quantum mechanics and particles and so forth, still you believe, I mean, there's a certain simplicity to electrons. Every electron is identical to every other electron. I mean, we don't have people. We can't say all people are identical to all other people. Every electron is literally identical to every other electron. And the systems that are studied by physicists are, in some sense, terribly, terribly idealized and terribly, terribly simple. And people are phenomenally complex. You might say, well, what about gases? Like a gas, 6 times 10 to the 23rd atoms or molecules in a container. And yet, that's very complex. And yet, look, it obeys Boyle's law. PV equals mkt, or something like that. Pressure times volume equals proportional to temperature. Well, the answer there is that once again, it turns out that even though there are so many, or it's actually not even though, it's because there are so many constituents, there's a sort of a canceling, and it's sort of the law of large numbers gives you a very, very simple behavior because these things are all identical and they're all crashing into each other in random ways, but the randomness sort of becomes more and more invisible as the numbers get larger and larger. If you had an ideal gas consisting of 10 particles, there would be no simple Boyle's law. But since it's 10 to the 24th particles, there is. And so even in a statistical mechanics, you get out deterministic laws. But for people who have 10 to the 12th or 10 to the 11th neurons and 10 to the 15th neural connections, there's no statistical mechanics that's going to... You can't simplify. Things don't cancel. There's no simplification that's going to come. And so inherently, people are just much more complex. And I think it's wonderful that occasionally people find some mathematical things that work a bit, like game theory. Prisoner's dilemma is an amazing model of a certain kind of dilemma that we find ourselves in from time to time. And it gives us a sense of understanding what's going on when people do things in certain kind of... Okay, one last question. There was somebody that I had pointed to, wasn't there? Well, I'll let you go ahead.
Thank you. What I was going to explore was the concept of the limit of analogy. I give you a couple examples like Einstein's work, Dirac's work, or Newton's work. When they studied the system, they didn't find anything analogous to describe that system. So Newton invented...
Totally wrong. Totally wrong. I'll just give you one example. Dirac, all of his quantum mechanics came out of an analogy between what they call Poisson brackets and commutators. So that's an analogy, and he spells it out in his own memoirs. It's absolutely an analogy. He says, I found an analogy between Poisson brackets and commutators. So that's Einstein. I could list thousands of, not literally thousands, but dozens of analogies that Einstein made, but I'll just give you one, only one. And it's for the discovery that he considered to be the most radical and revolutionary thing he ever did. And it was not special relativity, and it was not general relativity. It was what he called the light quantum hypothesis, and it was in 1905. And he generated the idea that light consisted of particles. And you have to understand that in 1905, people knew for sure that light was waves. It had been established by Young and Fresnel. It had been supported by infinitely by Maxwell's equations, and then by Hertz's experiments in 1889. It was known for sure that light was waves. There was no doubt about it in anybody's mind. But Einstein made an analogy between two systems. One system was the system called an ideal gas, which I've just mentioned briefly, and the other system was called a black body. And a black body was a cavity containing electromagnetic radiation, which I won't go into it anyway, at a certain temperature, just like the ideal gas would be at a certain temperature. Einstein knew he basically knew the spectrum, the energy spectrum. And I'm not going to draw this in any detail. I'm just going to say he just knew that the energy spectrum for each of these looked like this. I'm not going to tell you what that means. But he looked at these graphs and he said, there's something similar here. It's worth pursuing, this analogy between the ideal gas and the black body. And he then looked at the entropy of the two systems. I'm simplifying a little bit, but he basically calculated the entropy for the two systems and then manipulated the entropy expression until he came out with two equations, one of which had in an exponent the number n, which was the number of molecules in the ideal gas, and the other of which in its place had the energy divided by h nu being the frequency of the light and h being a certain constant. This is a constant, this is the frequency of the light, this is the energy in the cavity. I'm oversimplifying slightly, but anyway. And he said, the equations were identical. Exactly the same equation, except that one of them, the one referring to the ideal gas, had this, which is the number of particles, and this in the black body. And he said, gee, maybe that suggests that there are particles inside the black body, this many particles. In other words, the whole energy is being divided up into pieces of this size. And he published this result with 3 little appendices. The 3 little appendices were explanation. He said, if you want to test my theory, my hypothesis that light is made of particles, completely blowing all of 19th century physics into hell. I mean, you know, Maxwell's equations are out the window. I mean, light isn't waves anymore, it's particles. Bizarre. He said, if you want to test my theory, here's the 3 ways of testing it. And he mentioned one of them was the photoelectric effect, which had been ironically discovered by Hertz in the same series of experiments in which he confirmed that Maxwell's equations were correct. Light is a wave. But at the same time, he found a little glitch. He called it the photoelectric effect, and he published a few articles about it. Nobody knew much about it. And in the next few years, the photoelectric effect was studied very deeply by very many people, including Millikan in the United States. And Millikan in 1916 published a book about the photoelectric effect in which he said, Einstein's predictions for the behavior of the photoelectric effect have been fully confirmed by my experiments. However, we all know that the ideas underlying Einstein's explanation are nonsense. Even Einstein has rejected them. False. Einstein had never rejected them. And so he said, we have no way of understanding why it is that these predictions about the photoelectric effect came out of which came out of Einstein's light quantum hypothesis. We don't understand why the results match Einstein's ideas, because Einstein's ideas are crazy, as everybody knows. And no physicist in the world believed Einstein's ideas until 1923, when the Compton effect was discovered, and you can go read about it if you want to. And then all of a sudden, everybody flipped around, and everybody was a believer in light as particles. And it all came, believe me, read the article if you don't believe me, out of Einstein's analogy between the black body and the ideal gas. That's just one of dozens of analogies. Einstein's thinking, more than perhaps any other physicist, was pervaded by analogies. So, quick there. Thank you.
Okay, I would just like to thank Professor Hofstadter again for sharing with us these beautiful ideas about the role of analogies, and also for expressing them in such a beautiful and enthusiastic and charming way. And thank you all very much for coming tonight. Have a great day.